Hey, Jerry. Hey, Yaodong.
Hello，hi
Hey,
Tony，好久不见。
long time no see.
对
Really hope we can meet again in person next time at conference.
，Yeah，
Yeah, we'll give another minute for folks to come into the room, and then I'll start by introducing you. And all right, folks, let's start the session. So today we're glad to have Dr. Yaodong Yang, and he's gonna talk about multi-agent reinforcement learning. And yeah, and also welcome everyone to another session of Applied Reinforcement Learning seminar. So I'll start by introducing Dr. Yang. Dr. Yang is a machine learning researcher with 10-year working experience in both academia and industry. And currently he's an assistant professor at Peking University. His research is about reinforcement learning and multi-agent systems. He has maintained a track record of more than 40 publications at top conferences and journals, along with the Best System Paper Award at CoRL 2020 and the Best Blue Sky Paper Award at AAMAS 2021. Before joining Peking University, he was an assistant professor at King's College London. And before KCL, he was a principal research scientist at Huawei U.K., where he headed the multi-agent system team in London. And before Huawei, he was a senior research manager at AIG, working on AI applications in finance. He holds a Ph.D. degree from University College London and a master's degree from Imperial College London and a bachelor degree from University of Science and Technology of China. So welcome, Yaodong, and I'll hand you the floor.
Great, thanks Tony. It's a great pleasure to talk here. So I'm gonna share some of my recent research on the topic of training a population of agents. I'm affiliated with Peking U, and also I'm a visiting lecturer at King's. So let's get started. So when people ask me what I'm doing in the artificial intelligence or machine learning domain, I always like to quote this sentence from Alan Turing, where he says, if a machine never makes mistake, then it must not be intelligent. And in fact, you can find a lot of mathematical theorems trying to explain or elaborate this point of view from different perspective. But the interesting thing is, we should ask the question of how the intelligence emerge, or what kind of intelligence can we deduct from the system if the machine do make mistakes. And this is, I think, what reinforcement learning people or multi-agent reinforcement learning people are trying to model. So multi-agent problems are a little bit different from a traditional optimization problem. If you think of the optimization problem as the left-hand side, where you are going to optimize objective, and maybe you take some gradient descent dynamics following some gradient, and you end up with some minimum where the local gradient's norm is 0. And you search in this loss landscape. But on the contrary, if you look at what multi-agent problem is doing, it's kind of different in the sense that you have to take into account the change in your loss landscape, because you're playing a game with other agents, and the other agents is also reacting in the environment to your strategy. So in fact, you're dealing with a problem where the problem itself is changing. The simplest example is rock, paper, scissors. If your opponent keep playing rock, you can't say you can 100% solve the problem by playing the paper, because if you play paper, he will play scissors. So how to take into account the behavior from your opponents is a very different angle for multi-agent problem. So if you try to model multi-agent reinforcement learning problem, and I assume that people online in the Zoom room must be very familiar with MDP or single agent MDP. So what really makes multi-agent reinforcement learning different is that now, because in the environment you have multiple agents, so naturally you will have to consider different action space, A for different agent, and different reward function for different agent. And then you still have MDP's type of a process, stochastic process, where you would have the state space, transition function, initial distribution of your environment, and some discount rate. And if you consider the number of agents to 1, it decouples to single agent MDP. Or if you consider there is only one state, then it comes as what we call normal form game in game theory. And the goal for each agent is really trying to maximize its cumulative reward in the time expectation. But the different thing is, as I just said, you have to take into account what other people is doing. So this expectation over pi should be the joint policy, not only your policy. So you can define the vanilla value function, Q function, if you take into account other people's action by using the joint pi. And then the issue is, you can't really do a simple max to do the normal Q learning here, because you can't just think of your own Q function and maximize it. Think about the rock, paper, scissors example. You have to take into account what your opponent is going to play, rather than you only going to think of the current state and then maximize the current action. So what we should do instead is, you should really evaluate the current game at the current state, and then you try to solve the game. And depending on what kind of relationship you're in with your opponents, you can play cooperatively with your opponent, or competitively with your opponent, or something in the middle. So for a cooperative game, you can certainly assume that your opponent is going to maximize your reward. So you can safely take a max, because you know it is a cooperative game, and you know all of you share the same reward. So you can assume your opponent will maximize the Q function. Meanwhile, you're maximizing yours. And naturally, in the competitive game, because you play against your opponent, so you're in a competitive relationship with your opponent, so it should be a max min. And in general case where you have both a cooperative component and competitive component, you have to think of the general sum game, and you have to solve sort of some Nash equilibrium, and then use that equilibrium to guide where you should go. In this case, a common choice is you think of a Nash equilibrium. So a Nash equilibrium is nothing but just trying to say, okay, if every agent is doing the best response, it is doing their best to the rest of the agent, then it is a Nash equilibrium. So I will talk about this notion later with more concrete example. So the one big challenge that we meet in the multi-agent reinforcement learning is really the computation complexity of Nash equilibrium. And it is well known that computing even two-player Nash is PPAD hard. This really means that unless we can one day prove P equals to NP, there is no polynomial time solution. And the current best approximation solution to Nash equilibrium is that if you normalize the reward to 0 to 1, you will have this optional bounded to 0.3393. And recently, people has proved that this particular number is tight. So you can't decrease that number even further. And not only computing Nash equilibrium is challenging, but also asking any relevant property of Nash equilibrium is challenging. For example, if you want to compute how many Nash equilibrium is in your game, it is sharp P hard. If you want to check the uniqueness of your Nash equilibrium, it's NP hard. If you want to see if there is a guaranteed payoff for one player in Nash equilibrium, it's also NP hard. And this result applies on the case where you only have one state. For multiple states, it's even harder. For example, if you want to check whether pure strategy Nash equilibrium exists in a stochastic game where you have many states rather than one state, it's P space hard. So, but for reinforcement learning people, what we're dealing with is really not a normal form game. What we deal with is a game with multiple states, and you do have state transition between different states depending on the action from multiple agents. So you can think of a stochastic game like what the top right corner is doing. So at each state, in two players example, you will have a table in discrete action space. So the row equals to the action space of yours, and the column represents your opponent, and the number is the value at that state for that particular joint action pair. And depending on what action you take, it will go to different states. So you may think of, okay, we already know that solving one state Nash equilibrium is PPAD hard. Maybe you are thinking, okay, then if we consider multiple states, it must be harder, even harder. And recently we proved that, in fact, computing Markov perfect equilibrium, a special type of Nash equilibrium, in n-player stochastic game is still PPAD complete. So this means this problem itself is not harder. And this slightly gives multi-agent reinforcement learning people some hope that one day we can completely solve n-player stochastic game. But in reality, it is still very challenging that we can have a workable algorithm of perfect equilibrium in an n-player stochastic game. So instead, what we know is really only a small portion in the game space that we know how to solve. And I think I'm going to mainly mention our recent work on two phases. One phase is the fully cooperative game, and one phase is the zero-sum game, where we do know p-time solution in a normal form case. So let's talk about fully cooperative game, right? So why we end up here is because normal form game, we know it's hard to solve. General sum game is even harder to solve. Using reinforcement learning to solve these type of game, we know it's very challenging. So we focus on two specific type. So fully cooperative game. A fully cooperative game is a very hot research topic in multi-agent reinforcement learning because aligning or making agents cooperate to finish a job is a really common sense of framework, and it can be applied in many real-world applications. So fully cooperative game is saying, okay, each agent in the environment, they share exactly the same reward. So the first option you can come up with is to use a single agent learning algorithm where you can have a giant Q table by considering all agents' action into a Q table, as if you have a giant centralized controller. And then you can train this Q learning Q function using a traditional TD learning. But one thing with this approach is that it's not a really scalable approach because you would have to consider an exponentially large action space if you consider a joint centralized controller. And the beauty of applying multi-agent ARL method is it is decentralizable. So as a result, what researcher in our domain has been figured out is a particular framework called decentralized execution with centralized training. Meaning, if during training, I'm going to have some global information so that I can know this giant Q table, but during execution, if I can make sure that each agent can execute its policy based on its local observation, then this algorithm is somehow decentralizable. So one way to execute or to make the algorithm decentralizable is to assume the problem itself is meeting this condition, which we call individual global max condition in fully cooperative game, represented in this red box. It is trying to say, if we take the joint action maximization out of the total Q function, the giant Q function, if it equals to each agent take their maximization out of their own local Q function, then this problem must be decentralizable. And then you can train this joint Q function using normal Q learning, and then you can execute each individual agent's action by only look at his own Q table. So there are many algorithms that try to implement this assumption. For example, the VDN assumes the joint Q table equals to summation of Q local table, or the Q mix algorithm assumes there's a monotonic relationship between the Q joint and the Q individual. But this is not a panacea for all fully cooperative game. And in fact, by assuming the IGM assumption, you will meet a lot of problems, especially when the game has a coupled relationship between different agents. For example, if you have a fully cooperative game where the reward is to elect each agent's chosen action times your opponent's chosen action. For example, if you and your opponent are allowed to take one number from -10 to 10, and your reward is the number you choose times the number your opponent choose. And obviously, in this particular case, the largest reward you can achieve in this cooperative game is either you choose both 10 or you choose both -10. And for this type of problem, in fact, you can't use the IGM assumption to explain or even to model it, because your optimal action should always live on your opponent's chosen action. You can't just assume saying, okay, this Q joint equals to QI maximization. And following the some naive deduction, which I will omit here, you can easily find that this A joint total doesn't equal to each individual maximization. So to summary, people come up with this centralized training with decentralized execution method. They come up with this IGM condition, but for fully cooperative game where your action and your opponent's action are coupled, you can't really make such an assumption. It will fail. Okay, then you say, this is value-based method. What about policy gradient method? Admittedly, you can still apply a policy gradient method in multi-agent reinforcement learning. And as I just said, you can still do the centralized training with decentralized execution, where in the training, you train a centralized queue by considering not only your action, but also your opponent's action. And then you take your policy to update in the direction where you can maximize your joint queue function. But for policy gradient method, you will have two issues. One is the credit assignment issue, in the sense that, let's say if you find a way to optimize your pi, right? But then you are not quite sure where this improvement come from. It can be, there can be two sources where you can maximize your Q function. One is that you find a way to maximize your own action, your own policy, but it can be also another possibility that the improvement in your reward come from the the exploration of the rest of agents in the environment. So you can't really tell the difference between where the reward improvement come from. And a more serious problem is the huge variance issue. And in fact, if you apply this centralized CTD policy gradient, and then you analyze the variance of the gradient estimator, and you will find this centralized gradient estimator will have a much larger variance bounded by a term like this. And this term has two interesting factors. One is the number of agents, which is n. It's natural to think the more agents you have, the more exploration you will encounter in the environment, so the larger the policy gradient variance. And the other thing is this optional term, where it says the supreme of state minus AI and AI. It kind of represents the exploration term in your environment, where if your agents explore quite a lot, then you will have to suffer from even a larger a variance for policy gradient. So as a result, we can come up with some way to try to mitigate the huge variance for multi-agent policy gradient by using the baseline trick, as if you are in single agent learning, where you can also apply a baseline trick. So a baseline trick is a control variable that can make your policy gradient estimator stay unbiased, but minimize the variance. So you can minus a B term here, and then you can try to minimize the the variance of this whole GC term. And in fact, a very interesting baseline in multi-agent RL called COMA is a special case of this baseline trick, where you do minus the effect from the rest of the agents, and then you can focus on the contribution of your own action. But again, this type of baselines do have large variance, and we also did some analysis here. And the interesting you can do then is you can ask the question of, can we find out a baseline such that the variance of your policy gradient is minimized? And the answer is yes. So you can first write out the variance of the whole term of the centralized multi-agent policy gradient baseline here. And then you can do some simple analysis. You will find the variance, in fact, come from the state, come from the other agents' action, come from your own action. And the state variance, you can do nothing about it. The variance from other agents' action, you can't do anything about it either, but you can do something about your own action. So you can minimize the whole variance term by minimizing this term, and then you have an optimal baseline look like this. And then you can apply this optimal baseline back to here, and you can apply the MAPG. So the performance of applying the optimal baseline is very interesting. So we apply it on MAPPO, one of the recent very workable algorithm. On both some majority task and on some startup micromanagement task. And you can find by applying the baseline, the reward is keeping at the same level, but the training process is stabilized quite a lot. So to have a quick summarize, we have already seen the fully centralized version. We have seen that the value function-based approach using the IGM condition don't quite work well. And we also seen the policy-based method will have large variance and the minimum variance baseline. So you may ask, okay, can we find out a solution where all these problems can be solved? And the answer is yes. And before that, maybe we omit one even more naive case where you can just say, okay, the fully cooperative game can just be solved by making every agent share their parameter. but this can lead to exponentially worse outcome if the game is requiring you to do efficient exploration. So we show one counterexample key. So our solution is what we call multi-agent TRPO. So since people here have some ARL background, so I'm going to omit the background knowledge of what is TRPO in single agent case and jump to the most juicy part of how we come up with a multi-agent TRPO method. So TRPO method is powerful in the sense that it can have monotonic improvement guarantee. So if you follow the TRPO update, it can show you that the improvement in your loss function will be better than the previous step in every iteration. And how can we make sure that happens in multi-agent learning is questionable, and we don't know that. So in this work at ICR 2022, what we find is that you can actually make this work by designing a special kind of advantage function. And this advantage function is what we believe quite insightful to understand how multi-agent cooperative game should be solved. So we have to first introduce two notations where you have a Q function, but the Q function is different in the sense that you can choose what subgroup of agents, what subgroup of your opponents you want to integrate it out. And then following the same idea, you can define the A function. So A function in single agent learning means Q minus V. Here, we just use a different Q function. But remember, the Q function here depends on a special type of, a special subset of agents that you don't want to look at. So for example, here, you don't want to look at the contribution from the first agent to the mth agent, so you minus it. And what is interesting that by designing an advantage function like this, you can have an advantage function decomposition lemma. And this lemma does not hold, this lemma do not need any pre-assumption before it can hold. For example, the individual global max condition. For example, if you think of a two-agent case, you can decompose, you can represent this advantage lemma into a case where the two agents, their joint advantage function is state, the action for the first agent and action for the second agent. It can be decomposed into the first agent choose its action first, and then given the action from the first agent, the second agent choose his action. And this naturally holds in all fully cooperative game without any need for any assumption. And why this lemma is quite useful is because given this lemma, we can then design a simple protocol where we can make the monotonic improvement procedure possible. So the procedure is also very intuitive. So let's say, given this lemma, what we can do is we can let the first agent to take an action such that his own local advantage is bigger than 0. And then given the action he take, we can ask the next agent to take a new action to make sure his own local advantage is bigger than 0. And because we know this joint advantage function can be written as a summation of these local advantage function. And if each local advantage function is positive, then the summation is positive. Then we can know that the policy of the joint policy's advantage is improving monotonically. So we can use this red intuition to construct a multi-agent TRPO update. And you can design the normal surrogate loss as if you are in the single agent case, but remember you need to replace the advantage function using the local advantage function. And then you can design the TRPO update like this by make sure that the joint the agent's policy do not change too much from the previous policy. So then to make it to make the TRPO update into an executable gradient descent type of algorithm, you can still apply the natural policy gradient. And then you can have a policy gradient update term like this. And of course, you can choose not to look at or analyze this KL divergence term here and choose to use a PPO type of objective through a gradient clipping. And the interesting thing is, we can indeed improve, show that by following this TRPO update template, you can have a monotonic improvement property. And this is exactly what we want to see in multi-agent case, because this is the beauty of TRPO and why you apply TRPO. So we apply this algorithm on multi-agent module code task. In single agent learning, TRPO is working very well on continuous control tasks, like control a robot. But here, what we do is we consider the multi-agent module code task, where you really decompose a module code robot into different pieces, and each piece is controlled by a different policy. So you can see that, for example, this half cheater here, you can it has 6 joints, and you can really decompose it into 2 agents, and each agent controls three joints. And the yellow curve here is our method, and in almost all tasks, it has a significant performance benefit than the rest of the baseline, including MAPPO, which is a very well-known baseline recent days. So we also do a very interesting scenario where we try to use this MAPPO method to control 2 dexterous hands. So hands is a very challenging task because each hand has 25 joints, and both hands you have 50 joints, and you can't easily use a simple PPO algorithm to control it. It just doesn't work because 50-dimensional continuous control space is a very large space that needs decent exploration for modern ARL algorithm. So what we do is we model each hand and even each finger of each hand as different agents, so you can have different combinations. So the example I show here is two agents, and each agent controls 25 dimensions. And we apply this HATRPO on throw, lift up the pot, or push. And you can see it can finish the job very well. And we believe the advantage decomposition is a very efficient way to make agents collaborate, because if you think how your hands, or you really collaborate, your own hands operate in the real environment. For example, this throw, the left hand need to be ready to accept this object, and the right hand need to be ready to push, use your finger force to push the ball into the air. And these 2 actions need to be cooperated. And the advantage is nothing but tell you, okay, I'm going to, when I'm learning, I'm going to make the first agent take an action, and then the second agent is going to depend on what the first agent is going to take, and then take its own action, although the policy itself is fully decentralizable. So you can also put a safety constraints on the TRPO update rule, where in the environment you are asking, okay, during the learning process, can I ask a further problem where you don't want to visit certain states? So you can put a cost function on the state and action space where you don't want to visit, and then you can apply the same TRPO update and have a update rule where in the meantime you can have both monotonic improvement in reward and also both monotonic improvement in your cost function, which means you can make sure your policy is safe. So we test this constraint policy optimization in the module code case, the multi-agent module code case, where, for example, this spider has to move into this pathway without colliding into the red wall, or this cheetah has to run ahead without colliding into this red wall, and this red wall is moving. And you can see the cost for our algorithm is almost 0 after a short period of training, meanwhile maintaining a relatively good reward. So there are tons of details that I omit in this MACPO method. For example, how to use prime dual method to solve your objective. And I would encourage you to have read about this MACPO paper. But the main idea is still apply this advantage decomposition lemma, both on the cost function and on the reward function. Okay, so this is the recent progress on the fully cooperative game. And the next half I'm going to share is on the fully competitive game, the two-player zero-sum game. And in fact, maybe the zero-sum side is what makes a multi-agent RL technique more well-known, given these very remarkable progress being made on game environment, such as StarCraft, Dota, Capture the Flag, etc. So in zero-sum game, our target is that given any black box multi-agent game engine, for example, a chess engine, where it takes two policies in as input and output the reward, whether player one beats player two. And your goal is really to design some algorithm such that it can give you some policy that is a low exploitable. So what does it mean by low exploitable? So think about two-player zero-sum game. Your only target is, in fact, to try to not lose, right? So what does it mean by not lose? Meaning, given my current policy, I cannot find a further policy that can beat me, or I cannot find a further policy that can achieve positive reward upon my current policy. So if your exploitability is zero, meaning that you cannot be exploited, and if both players' exploitability is zero, it means that you and your opponent are reaching a Nash equilibrium. So a challenging problem in training or designing two-player zero-sum game solution is what we call this non-transitivity. So non-transitivity, maybe we can start from the symptom of the non-transitivity. So take this soccer as an example. So you are trying to solve a soccer game where you have a player, and this player output a policy to control a team of 11 members. So you train some players policy A, where you can beat your built-in AI. And then you can treat another, and then you can train another policy B that can beat your current policy A. And then the non-transitivity will lead you to a very interesting symptom that you can find that policy B can no longer beat the built-in policy. And such phenomenon also was observed on training StarCraft, where during training, if you keep using self-play during training, you will have a very high error ratio. But if you use your recent model play against its own previous version, you can find the winning rate is not that high. So non-transitivity really means that in your game space, the policy itself is counterfacting each other. So you will not have a consistent winner, but rather each policy is better than the rest of the policy, and you're locked in a cyclic cycle. So this cyclic cycle, and understanding this cyclic cycle can really help you understand how to come up with a highly efficient two-player zero-sum game solver. So this is the game that we have been taken from a paper from the spinning top type paper. So the red rectangle, what it shows is that when people are trying to solve the StarCraft, they have trained 888 policy. So you can think of it in the left plot where you have many days. From day 1, you have 0 model, and then to the day 14, you have 600 models. And then if you consider how many, if you compute this, the Nash equilibrium of your 888 model, so you have a square, row is 888 rows, column is 888, and the number is the winning rate between each pair. So you compare, if you consider the Nash equilibrium of this matrix, you will find there is only 3 strategy out of 888 that has a non-zero probability in your Nash equilibrium. So it means that a lot of those strategies are wasted during the training time. And if you can know beforehand, or if you can come up with a more efficient training algorithm that can give you the 3 strategy, but of course you don't know which 3, but even if it can help you shrink the exploration phase in the policy space, then you can save a lot of time. And this means a lot of training power, because each policy is takes a full RL cycle to to find during your training phase. So a very interesting research from DeepMind is this hypothesis they've been putting up with. They're saying for any type of two-player zero-sum game, it somehow will show this geometry where the x-axis showing you the non-transitive dimension. You can think of the non-transitive dimension as the dimension of how each strategy counterbalance the other. So for example, in rock, paper, scissors case, you have 3 strategies, and each strategy counterbalance the other 2. So then the dimension is 3. And the column axis is the absolute strength. You can think of it as the L rating. So what a human learns, or what an AI learns to master a game, is really starting from the bottom of this plot and then go up to the top of the plot. But you have to encounter a phase where the non-transitivity dimension expands. So think of how you play a game, for example, some mobile game. You start with some naive strategy, though it is very naive, but the non-transitivity dimension is also very low because it's really hard for you to lose to everybody, right? By luck, you can always win 1 or 2 games. But with your increasing dimension of transitivity, your strength, you will encounter a phase where your non-transitivity dimension start to expand. This also meets with what human learns, because when you try to master a game, you may find sometimes there are different heroes, or there are different species or different strategies that you can play in the game. And then you will find there are actually many, many of them, and each of them is counterbalancing the rest. But with your capability improving, you will find this dimension actually start to decrease. Because if you ask a professional level player what kind of strategy you play, he may not always tell you a particular strategy he will play, because he have already seen all kinds of different ways of playing the game. He will ask you, okay, the only tactic that I can master is really depending on what my opponent is playing, I'm going to choose correspondingly. There's no particular strategy. So the non-transitivity at the professional level is also start to shrink and become very low. So what we need to design an AI algorithm to solve two-player zero-sum game is really working from the bottom of this plot to the top of this plot. But you have to come up with some smart ways to jump over the red area quickly. So this geometry hypothesis has also been tested on human chess players. So we take 1 billion records from live chess platform, and we try to map the non-transitivity dimension with the L rating. We try to see whether the spinning top hypothesis does happen on human player. And interestingly, it does. So the left plot is the L rating histogram of all live chess players. And the right-hand side is the a specific metric of non-transitivity of different live chess player. And you can see the peak happens on the L rating around 1700. And this is also the peak where the non-transitivity is hits its maximum. So in human players, then if you can jump over the non-transitivity area quickly, then we believe you can improve your skills quickly. But how? So if you look at how game theory people look at this problem, remember that in the rock, recall that in the rock, paper, scissors case, if you only look at the current strategy of your opponent, right? For example, if he's playing rock, then you play paper. If you play paper, he plays scissors. If you only look at and keep focus on the latest strategy that your opponent is playing, then you'll end up with nothing but a cyclic rule. So what game theory people and machine learning people come up in 2003 is an algorithm called double oracle, where it tries to say, okay, I'm not only going to look at the latest strategy of my opponent, but rather look at the natural equilibrium of my opponent strategy. So you're going to make a record of all the strategies that your opponent has been playing. And then you are going to compute the Nash equilibrium of your opponent's strategy, and then you're going to take a best response. So the algorithm is super simple, where given the current game A, you compute the Nash equilibrium of your current opponent in yourself, and then you find a best response of your opponent's Nash equilibrium, and assuming your opponent is going to find the best response of your current Nash strategy, and then you put both best response into your population pool, and then you expand your policy. And you can show that by iterating like this way, you keep expanding your population pool, you can finally reach the whole Nash equilibrium of the original game. So when the process stops, meaning there is no further new best response I can find, you can prove that at that moment, it is the Nash equilibrium of the whole game. So when in the double oracle process, if you plug in an ARL subroutine to help you find the best response, it is called policy space response oracle, meaning in the policy space, you are going to use reinforcement learning algorithm to find a best response and use that as your oracle. So the algorithm is very similar to the double oracle, but you need to replace a best response training against the opponent using a reinforcement learning subroutine. And then you add this newly discovered policy into your population pool, and then you compute the Nash equilibrium and you start to loop again. And depending on how you sample your opponent, for example, if you're only going to consider the latest policy, it's the self-play. If you're only going to consider the time average weights of your opponent's play, then it's fictitious play. And if you're going to compute the Nash, then it's the double oracle. So you can think a framework of how you solve a two-player zero-sum game as a plot like this, where you have a pool, right? You start from only one or two strategy, and then at each step, you try to find a new strategy, and then you add it into your pool, and you expand your pool, and in the end, you hope the strategy pool will give you a very low exploitability rate, meaning you cannot be beaten. And how and what is happening in the pool expanding process is really, you first evaluate what your opponent is going to play. Either you keep focus on the latest strategy, which will not converge, or you keep focus on the Nash equilibrium of his strategy, or you focus on the time average of your opponent's historical strategy. And then you apply reinforcement learning subroutine to find the best response, and then you expand your policy pool. And then until your computational budget allows, you can output the whole pool, and with the weight decided by the Nash equilibrium of that pool, you can reach a low exploitability. So a question to ask is, can we use machine learning algorithm to design these two orange rectangles, i.e. using some learning to learn method to discover the algorithm, rather than we use some game theoretical subroutine or using some ARL subroutine to solve the game? Because all the previous, not only including double oracle or the PSL method, we have to rely on quite a lot on game theoretical prior knowledge or a reinforcement learning prior knowledge. So if we can let the algorithm learning to learn these two orange rectangles, then you can make the AI solve the two-player zero-sum game by itself. And the solution to learning to learn those two orange rectangle is what we call the neural autocurriculum. Recent paper we published at NeurIPS 2021. So in two-player zero-sum game, the key question that we need to answer is who to beat and how to beat them. It's exactly what those two orange rectangle is trying to say. So you have to take into account the non-transitivity, because strategy counterbalance each other. And when you try to solve these questions, who to beat and how to beat them, you have to take into account non-transitivity. But then how can you design this curricula? can you use meta-learning or learning-to-learn method to let AI find it by itself? So this is, in fact, in line with some recent progress from meta-gradient reinforcement learning, where in single-agent case, they try to use meta-learning framework to find, for example, a correct loss function for TD learning or correct loss function for policy gradient, rather than use dynamic programming principle. And it turns out to be quite effective. So what we try to do here is this propagation throughout from the first step, from the last step to the first step by minimizing your exploitability. Because the only goal you try to reach here is to minimize the exploitability of your population pool when you try to solve the two-clear zero-sum game. So there are many processes that get involved into this procedure, including, for example, how you represent the payoff matrix, how you compute your opponent's distribution. In normal case, it should be Nash equilibrium, but here we decide to represent it using a different neural network. But then you need to consider like permutation, invariation, these kind of property. So I will not go into the detail of them. And you also need to take into account how can we design a best response oracle using some neural network method, for example, gradient descent or policy gradient. And then how you design your learning objective, which should be your exploitability. And then how you take the gradient of your gradient back from the last time step policy pool to the first time step policy pool. There are many details get involved, and you need to be super careful about the gradient here, because remember this process here, if you try to take back the gradient, this blue circle is a process that already involves gradient, and so does the green circle, the green part, and so does the blue part. So when you take the gradients back, you have to be very careful about what algorithm you choose to represent this blue and the green circle, and then you need to choose a gradient of gradient that is compatible with these two steps. But by virtue of backpropagation nowadays, you can do it do this part easily. For example, if you use one-step gradient descent oracle as the green part, this is the meta gradient. If you use n-step, you have to consider implicit gradient. If you use policy gradient, then you have to use the gradient of policy gradient and some other non-gradient method. So there are many gradient-based details I will omit here, and I would strongly encourage people to have a read of our paper. But the main idea is that we try to represent this blue area and then this green area using neural representations, and we try to learn what should be the best format of these two areas. So the result is in fact very inspiring. So the output of the previous neural autocurricular framework is an algorithm, and we believe that algorithm can help us or can lead us to solve zero-sum game. So we apply that learned algorithm on solving different type of zero-sum game, and the y-axis is the exploitability. And what you can find is that our algorithm is performing no worse than PSR method, where we have to live on game theory and a lot of ARL basics to design. So, and even in some cases, our algorithm is performing better than PSR method. So you may wonder, okay, why AI can figure out an algorithm that is even performing better than human knowledge. So we believe is that because in the whole process, the best response that you take is given by a reinforcement learning subroutine. So it's very hard to guarantee that if you keep strictly following a game theoretical knowledge, for example, computing a Nash equilibrium, it will surely give you the best option that you can take in designing the curriculum, because the best response is not exact best response, but an approximate best response by our oracle. So it's just like what we have shown here. So we try to plot out what the algorithm has actually learned during the process. So the first row is a normal PSL autocurricular, a PSL curricula would give you. And the second row is what we learned. So the star is the new best response that each iteration has found. And the rest circles is the probability weight of how you train against your opponent. The darker, the larger the weight. So as you can see, with 10 iterations, oh, by the way, the game is multi-dimensional rock, paper, scissors. You can think of rock, paper, scissors as a 3 mode in the continuous space. So here we make it the problem even harder to make it 7 mode. And the trick here is really to explore all modes rather than overfitting on one mode. Otherwise, you will lose the other modes. So at the 10th iteration, what you can find is that the algorithm that is learned by the neural autocurricula promote exploring the modes. And this promotion is compatible with the best response dynamics that it tries to discover at each iteration. But compared to the PSL method, because the best response is not the exact, and this error in the best response approximation leads to the failure of using a normal Nash equilibrium as the opponent selection procedure. So we also test the algorithm and try to apply the algorithm directly across different games. So we, for example, on one type of poker, we run neural autocurricula. We find one algorithm that can solve the coin poker, and then we immediately apply that algorithm on Leduc poker. And it's a new poker. And we want to see whether the learned algorithm can indeed generalize across different type of game. So we apply this learned algorithm on coin poker, from coin poker to Leduc poker. And we also plot out the exploitability. As you can see, the red curves keep decreasing with the training iterations goes on, which means the learned algorithm is an effective algorithm that can not only solve one type of poker, but also solve similar type of poker. And also we tested on a normal form game with different dimensions. For example, here, we train, I think, the neural autocurricula on a 250 dimension, and then we apply the learn algorithm across various dimensions, including 1500 dimension. And you can see the exploitability is kept at a very low rate, regardless of the changing of your dimension, showing again the generalization capability of the neural autocurricular that the algorithm learned by itself. So far, I've been talking about mainly the population-based method, where at each iteration, you do have to take into account the way you add a new ARL agent into your population, and in the end, the whole population becomes unexploitable. So there's other big chunk of method where I haven't touched on solving two-player zero-sum game, which is search-based method. And in fact, these are the key method on solving poker or solving a game like Go, especially when your game tree is searchable. And all these type of game like StarCraft, the game tree is not really searchable. So you can apply a search-based method, CFR, counterfactual regret minimization, for example. And you may wonder, what's the difference between these two type of methods? On the left-hand side, you have PSL method, you have neural autocurricular type of method. You use ARL algorithm to find new policy at each iteration. You try to expand your policy pool. On the right-hand side, you have some no-regret method, CFR method, MCTS, where you try to make sure the regret in the time limit becomes 0. And you can approximate best response. And these two methods seem to be so different. And in fact, you can come up with some method that try to take the merits from both worlds. So due to the time limit, I will jump over this part, but you are encouraged to read our paper called Online Double Oracle, where we try to introduce a new version of double oracle by taking into account this online learning essence into the double oracle procedure, and enjoy the benefits from both being a no regret method and can guide you to a population-based training framework. And it applies on both extensive form game and non-extensive form game. So the last bit I want to introduce is that there are many practices on solving two-player zero-sum game. And from the day one, where our group is one of the first groups that try to look at the StarCraft problem, where by that time only 1 to 2 GPUs training 1 to 2 days can solve the problem, to most recent practice a mobile type of game where you need almost astronomical number of CPUs and GPUs and train for ages to solve the game. What really matters is not only the algorithm, but also a pipeline, but also a platform which can help you execute the distributed multi-agent ARL algorithm efficiently. So what the population-based method requires on top of normal distributed ARL is what we call league manager. And this is where this opponent selection module, game evaluation module, including other type of property module like diversity, policy diversity module happening. So when we try to develop this whole practice around PSL, including neural autocurriculum, we do not find one such type of open source platform that is available that can support single agent, multi-agent, and population management. So we decided to build our own. So the key requirement is that we need to have an extra module where the task level rollout and the game level evaluation can be maintained separately. So we developed this what we called MALib, and it's specifically designed for population-based MARL. So in short, you can consider it as a library where it can give you all kinds of independent learning method to represent each player, for example, DQN, A2C, DDP, GTRPO. But they can also do self-play or PSL play or fictitious self-play, in the sense that you can choose a basket population of your opponent's model, and then you can find a new best response, and then you can expand your policy pool. And in the end, hopefully you can have a low exploitability. So we open source this MLab with all the PSL type of developments that we have been making, and put the sample code there. And we encourage people to have a run about this MLab library. So to summarize, we've been starting with what is learning, what is intelligence, the Alan Turing's quote. But we also point out that in multi-agent learning, computing national equilibrium is very hard. And this makes multi-agent learning problem very hard. But also we show you one kind of promising result that solving the Markov perfect equilibrium in unplayer stochastic game is in fact PPAD complete, meaning it's not even harder than we might think. And then we focus on two types of games. One is fully cooperative game, one is zero-sum game. And in the fully cooperative game, we've been looking at different options, value-based method that maintain IGM condition, policy gradient method that might suffer from a large variance. We introduce you one baseline trick that can minimize the variance. But what really matters is what we believe that MATRPO method, where it leverages the powerful advantage decomposition lemma to give you this MATRPO method that can guarantee monotonic improvement in performance. And then on the zero-sum game side, where we have been looking at the non-transitivity issue, where in the policy space, you would have to, or you will inevitably encounter this policy counterbalance issue, others phenomenon. And how to solve that issue is really by looking at not only the current policy of your opponent, but also a basket of your opponent's policy. And you can consider a Nash equilibrium as the opponent selection module. And we also show you that it is completely possible that we discard all these game theoretical knowledge or reinforcement learning knowledge by making the algorithm a learning to learn a solution framework. And we've shown you that the discovered solution framework can in fact generalize across different tasks. And this is what we call neural curricula. And finally, we put these PSR type of method that we have been developing, including neural curricula, into MLib, and we encourage people to have a look. And with that being said, I think I can conclude and I can finish this talk today. Thanks.
Thank you, Yaodong. Thank you so much. Really interesting topics and a lot of impressive results. I think all of us have learned a lot from this single session. Are there any questions from audience online? Let's first of all look at whether there's a question there. Yeah, I actually have a couple of questions. So first one is regarding the neural autocurricular. So how do you actually train the neural networks for the two modules that you have to substitute the PSR in that framework, like the neural meta solver and the one for solving the best response? Do you train the neural networks in a separate instance, or is it like trained more in the end-to-end fashion?
Yeah, thanks for the question. Yeah, it's a great question. So in fact, what we do here is we try to represent the blue area and the green area. So the blue area is trying to say, okay, given the current basket of policy, how can I select or how can I evaluate the current policy pool such that I know which enemy I should beat? So in normal setting, here should be a Nash equilibrium. I mean, the whole blue area. In double oracle's case, it should be the whole Nash equilibrium. And then in the green area, it should be given the current Nash equilibrium of the policy pool, I'm going to find a way to optimize against that pool. You can use gradient descent, you can use policy gradient, and you can use all type of gradient or non-gradient involved algorithm. So, and then you find a new policy, and this new policy should be put into your original policy pool to expand the policy pool. And then you keep doing this process. And in the end, you will have a loss function, which is the exploitability of your whole population, because you can always evaluate the exploitability of your whole population by computing, can I find a new best response that can beat my whole population? If it is 0, then good, meaning you cannot be further improved. And then if you represent this blue area and the green area with neural networks, for example, the blue area, what it does is input a payoff matrix, output some distribution for each player, because this is how you evaluate the current game. Although the unit here is a policy, not action. And the green area is some best response oracle. For example, you can use one-step gradient descent, but it's too naive. But you can also consider more complicated green optimization subroutine like n-step gradient descent or policy gradient, TRPO, PPO, as the green area here. And then you can put everything together by only minimizing the exploitability. The parameter of your green area and your blue area will get involved. And then you have to be careful about the gradient when you try to train it end to end, because each process. So in fact, I've put an arrow here. So when you take the gradient back, there are like 5 areas where you will have the gradient of gradient, because each step, although you will add only a new strategy at each step, but this new strategy depends on how the strategy is added in the previous step. And then you need to expand the whole nested structure. So to answer your question, it is trained end to end, and you need to be careful about the meta gradient getting involved.
Okay, gotcha. And another question is regarding the previous topic, the multi-agent for the fully cooperative games. So in your computation of the global advantage, it seems to me that there's implicitly induce sequence that that you have selected upon the agents, and you compute the local advantage. Is that sequence important? Like, does it matter? And does that break the property of decentralization?
Yeah, it's also a very nice catch. So I've omitted a lot of details here. So in fact, the sequence doesn't matter, and the sequence has to be randomized before you can guarantee the monotonic improving property. So we actually have showing a proposition that this sequence, so the first agent and the second agent, this agent sequence number should not be binded with the agent number in your environment. So for example, agent 2 or player 2 can sometimes in the iteration be your first agent, and in the next iteration be a second agent. And this cannot be coupled. So, and also we believe have a randomized agent sequence number would also help you do efficient exploration. Yeah, so it is both necessary and sufficient. Yeah.
Okay. Cool. Yeah, if there's no more question from the online audience, and for the interest of time, I think we can close the session here. Let's thanks again our speaker, Dr. Yaodong Yang, and thank all the audience coming to the session today. We hope to see you again for the next session. And,
thanks again, Tony.
Thank you.
Bye-bye.
Bye.